Epilepsy is a neurological disorder defined by sudden bursts of synchronized neural firing. These pathological synchronization patterns produce the uncontrolled electric waves that result in seizures. Current treatments include pharmaceuticals, electrical deep brain stimulation, and optogenetics, but these options struggle with imprecision, invasiveness, or the need for genetic modification. Our proposed solution is a neutral stimulation using optoacoustic absorption, which harnesses light-generated ultrasound waves to mechanically activate neurons with extreme high precision.
The optoacoustic effect converts pulsed light energy into ultrasonic pressure waves. The mechanism requires thermal and stress confinement. When a nanosecond laser pulse strikes the absorbing material, rapid localized heating occurs faster than the heat can diffuse or stress can propagate. The heated region then undergoes a rapid thermoelastic expansion, launching outward propagating pressure waves. As demonstrated in the 2022 Neurophotonics review by Shi and colleagues, a 3 nanosecond pulse laser at 1030 nanometers, striking absorbing agents such as gold nanoparticles, carbon nanotubes, or graphite, generates acoustic pressure waves of approximately 0.5 megapascals. Their research demonstrated successful neural activation in cultured rat cortical neurons and in vivo mouse cortex, which we are extrapolating to humans today. Figure 1b shows 3 optoacoustic platforms for neural stimulation: fiber-based emitters, biocompatible films, and injectable nanotransducers, each employing the same principle with different geometries. This combines optical spatial precision with ultrasound tissue penetration, allowing precise neural modulation without genetic modification or electrode implantation.
Optoacoustic imaging is promising due to its less invasive properties and its precise ultrasound-like waves. This phenomenon allows us to inject nanoparticles into tissue and activate it via laser optics. For example, our device will involve injecting gold nanoparticles into areas of the brain that require neural stimulation. As seen in our schematic, our device will then provide near-infrared pulsed laser light to the targeted area. This laser uses non-invasive, unharmful light, but is still strong enough to cause rapid heating at the nanosecond scale to the gold nanoparticles in the brain tissue. The laser light triggers optoacoustic absorption in the nanoparticles, turning the thermal energy into pressure waves that are generated in pulse-like frequency. These pressure waves have been proven to mechanically deform the nearby neurolipid membranes by altering the tension. The deformed lipid membranes then activate the contained mechanosensitive ion channels in the neurons, such as the piezo and TRP channels. Shown here in this diagram, the stimulation of these mechanosensitive ion channels depolarizes the neurons, triggering a neural action potential. The stimulated neurons are only those that are in close proximity to the nanoparticles that are injected, as the membrane would require enough pressure to depolarize. Given these findings, our device is able to non-invasively stimulate select neurons in the brain at determined frequencies. This is a huge development in the medical and neurological field and can have many different uses and applications.
Epilepsy arises from imbalanced brain activity. Excitatory neurons become hyperactive while inhibitory circuits fail to compensate, causing thousands of neurons to fire in synchrony like crowd clapping in unison. Our device disrupts this pathological synchronization through 2 mechanisms. First, we hypothesize that optoacoustic stimulation of nanoparticle-labeled regions can be used to mechanically activate GABAergic interneurons. The resulting pressure waves open mechanosensitive ion channels, increasing GABA release and strengthening inhibitory control to counteract uncontrolled excitatory firing during seizures. Second, precisely timed ultrasound pulses delivered in offset spatial and temporal patterns introduce controlled phase shifts across neural networks. This coordinated reset stimulation disrupts the synchronized firing that drives seizure propagation. Animal studies show this approach reduces synchronization across multiple frequency bands, lowering amplitude, spectral power, and phase locking. Computational models demonstrate that repeated desynchronization weakens pathological synaptic connections through spike timing dependent plasticity, promoting lasting network reorganization through stability. Our device overcomes 2 key limitations of current therapies. Electrical stimulation lacks spatial specificity, while optogenetics requires genetic modification. Using optoacoustic nanoparticles enables precise, non-invasive neuromodulation without electrodes or viral vectors, offering targeted intervention for epilepsy treatment.
Optoacoustic neutral stimulation offers a precise, non-genetic, minimally invasive way to control neural activity. This method benefits those with epilepsy by preventing seizures, strengthening inhibitions, and disrupting pathological synchrony. This technology also has potential to be applied to Parkinson's disease, depression, vision restoration, and even high-resolution neural prosthetics.